So welcome back to our Integral Calculus Quick Start Guide. Number 5, finding the area under a curve using summation. And you ask, what does summation have to do with any of this stuff that we're dealing with? Well, let me show you where this leads. First of all, our main task, one of the main tasks of integral calculus is being able to find the area under a curve. How do we do it? Well, one way might be to estimate that curve, right? So the area is what we're interested in under the curve, and one way to do it is maybe divide up the area into something easier to deal with, like these rectangles right here. Now you recognize that the area of a rectangle is going to be equal to length times width, or height times width. So let's focus for a moment on this blue rectangle right here. What could we say? Well, if we're interested in the area from A to B, in this case, let's make it A to B over here, and we want to estimate it using the summation of these rectangles, then what we're going to do is we're going to divide up the area into some number of rectangles, right? So we'll say that the width is evenly divided. And that width we're going to call delta x. And we're going to take b minus a, whatever those numbers are, and divide it by the number of rectangles that we have. Okay, so what does that mean? That means each of these rectangles has a width of delta x, and they're all evenly divided. So that's a helpful thing for us, because then we don't have to worry too much about how big each of those rectangles are. What about the height? Well, depending on the way that we define the area of each of these rectangles, like for example, the forward leading edge of that rectangle is going to be the height of the function itself at that point x, at that trailing edge right there. So I'm going to call it f of x asterisk right there to kind of represent that. And what we say then is that the height of that particular rectangle, the blue rectangle, which is just some arbitrary rectangle in the middle, is going to be an area equal to f of x asterisk times delta x. That's a little asterisk right there, not a very good one. But anyways, that's the area of that one. Well, it doesn't matter how many rectangles we have. In this case, 1, 2, 3, 4, 5, 6, 7. There would be 8, but its height is 0 over here, right? I'm going to put that over there. But if we add all those up, then we're going to get that area. So how do we do it? Well, we could say, well, all right, f of x1 times delta x plus f of x2 times delta x plus and on down to the last rectangle. Let's call it rectangle n times delta x. That would be the approximate area. But we also like to use this notation, the sum from I equals 1 to n, let's say, of f of xi times delta x. And so that x asterisk right there, in this particular case, x asterisk, would be our x of I right here. And if we add all those up, we're going to get this sum. Now, it depends on which one we want, right? Sometimes the sum will be overestimate, and sometimes it'll be an underestimate. We can see in this particular case that this particular one is going to be an underestimate, whereas this one's going to be an overestimate. How do we know? Well, look at the rectangles, right? They all either sit above or all below that curve. And we could have curves where there could be some above and some below, so we're never quite sure. So instead, what we're going to call this one, where this leading edge right over here is the case, these are right rectangles, because we're doing the right side of the rectangle as the height, so that's going to be a right sum. And this one, where the left edge, the trailing edge, defines the height of each of those, we can call this a left sum. And so in summation calculus, you sometimes do that, this summation thing, in order to get it. However, Rather than dwelling on the notation and the methods of finding sums for areas under the curve, let's just note what this means to us. If we take the sum of some areas, if we have more rectangles, we can see that our area is going to be better than if we have a few rectangles, right? So if we can increase those number of rectangles indefinitely and get an infinite number of rectangles to add up using our summation, then provided that that sum exists, provided that limit exists, what we really get is called the definite integral from a to b of f of x dx. And this is where our integration symbol starts getting used.